Welcome, Eli and Ralph and Eduardo, RC, Jacob, Evan, Kristen, Victor, Max, Nikki, Jade, and Jesus. What we're talking about today, let me share my screen so I can go over the plan, is I'll start out with going over the quiz as soon as I talk about what we're doing today. And then we're moving into calculus. So it's been a while. We haven't really done any calculus for weeks, but now we're going into calculus. And we're kind of going in order of the way you do calculus when you first learn calculus. So we're going to start out with limits today. Okay, so we're going to do the definition of a limit. And this is something you may or may not remember, but it happened, I know, not by me, but by Bruce. And we'll talk about, what does it mean to be a limit, but not a limit like you had 2 quarters ago where it was a function of x, but now we're going to look at a function of x and y. So things get a little more complicated. And we'll talk about easy examples of finding a limit, and that doesn't get complicated. That's the good news. And after that, we'll talk about how do you prove that a limit does not exist. Okay, and that was a little bit easier than proving a limit does exist. We'll have a nice theorem, though, that helps us out a lot. Then we'll look at the next step in calculus, and that is continuity. So what does it mean for a function of 2 variables to be continuous? Okay, and finally, we'll get into what happens when you have a function of more than 2 variables. But if you have 3 variables, can you find a limit? Can you talk about continuity? And it turns out it's the same, but just one more letter to write down. So that is the plan of the day. Hopefully that makes sense for all of you. Again, we're moving into calculus now, as in we've spent a lot of time looking at analytic geometry, and now we're back. So we're back to limits. And any guess on what we're going to be doing in a couple days?
Integration?
Integration didn't come next in calculus. What came next in calculus?
Derivatives.
Derivatives. Okay. And in fact, integration is particularly difficult, but here's the good news. We don't do that in this class. So we don't integrate functions of more than one variable. We do have a day on review of integration from last quarter, but we don't do any of the integrals. That's next quarter. And some of you will take next quarter, some won't, but those who do, you'll get into the integration. But we're not going to do that. So what we're going to do is we're going to do derivatives after this. So Wednesday, we're going to spend a bunch of days on derivatives. And then we're going to go back to a special case of limits. In particular, we're going to be looking at series. And that's the last half of this class, so I'm not talking about it. Are there any questions about anything that you might have? Okay. I do want to mention, again, feel free to ask questions, but I want to mention this quiz was not on Proctorio. It does not mean you never have to use Proctorio again. What I decided was last week, since we weren't doing calculus, it wasn't too hard, and there was no uploading of graphs or anything like that, which doesn't work as well on Proctorio. I decided to embed some Proctorio so that everyone would get the Proctorio experience and figure out if your computer can handle it or not. Okay, so, but let you know your exam, which is in, I think, 2 weeks, something like that. Your exam uses Proctorio, and unlike the quizzes, it's high stakes. So you have to get that working. So I haven't done it yet, but I'm gonna set up a practice Proctorio test, just for those who want to practice, making sure if you're still getting stuck. But don't assume that now that we're not doing Proctorio, it doesn't mean you never have to do it again. We did it last week to prepare you to see if you're ready. And if your computer did not work for Proctorio, it means you need to get a computer from the library. Okay, and the library's got them. They're free. Please pick one up. Okay, they said they still have some. So definitely that's what you do. And I can give you the referral. Just have to ask me, and then I'll send them an email. So make sure you get that done. You don't want a disaster happening, which means that you can't get into Proctoria, which means you can't get into the quiz on, the exam when it happens. So that's a big deal. So, and I'm here to help you out if you have any issues with computer. If you had any issues, I can help you out. And like I said, the biggest help is get another computer, which is free. Okay, any questions before we jump to the quiz? Okay, so let's do the quiz. I'm going to start here and then we'll actually have to leave here a little bit. Okay, so find the level curve for the function f of xy equals the square root of x squared plus y at the value c equal 1, then 2, then 3. Sketch the curve by hand on a piece of paper labeled with the corresponding c values and attach it to this question. Okay, you're not allowed to use any technology to solve this problem. All right, so what we're going to do, and again, you always want to show work, is the first thing we do is let's write down what these curves are. So let's start with c equals 1. For the c equals 1, where do I put the number 1? So when we say c equals 1, where does that 1 go? Yeah, so I replace f of xy with 1. Okay, and so let me write this down. Okay, so now what I do is I'm going to do it with the equation editor. We can say 1 equals the square root of x plus y. Okay, now I'm going to have to graph this, so I think it helps to do a little algebra. Square both sides and subtract x squared. And you get y equals 1 minus x squared. And maybe I'll write c equals 1. And let's do the go. Any questions so far? Okay, so now I'm going to do c equals 2, because I was supposed to do 1, 2, and 3. I'm just going to copy and paste this guy. It's one good thing about typing versus writing is that you can copy and paste really easily. So now we're going to do c equals 2. And we have 2 equals the square root of x squared plus y. And notice we square both sides, the 2 becomes a 4. And you get 4 minus x squared. Any questions so far? And then I do the same thing with c equals 3. So I'm going to copy and paste, change the 1 to a 3. And then when I square both sides, that 3 becomes a 9. And we get y equals 9 minus x squared. Okay, now here's something you should all know, I hope, is what is the graph of y equals a number minus x squared?
That's an upside down parabola.
Yeah, it's a parabola. I'm going to use the calculus words, a concave down parabola. You could say upside down, but I'm going to be, since this is a calculus class, it's a concave down parabola. And the 1, 4, and 9 will help us figure out where the x-intercepts are. In fact, the x-intercepts are going to be this plus or minus the square root of those 3 numbers. Any questions on that? So the interesting thing is the x-intercepts are the values of c. Any questions on that? So now, I know I told you to do it on a piece of paper, but it's too hard to do a piece of paper with a video camera and you seeing it. So I'm not going to use a paper. I'm going to use my drawing tool. And technically, if you use a drawing tool, I'd be okay with that. But paper's a lot faster. But for teaching purposes, Okay, so what I got is, let's draw some axes. And let's just put out, we gotta go -3, -2, -1. One, two, oops, 2, 3. Make it a little bit higher. That's good. Just kind of label them. And what we've got for c equals 1, let's do a draw. Is we got a parabola. Concave down, again, it's not perfect, but I do my best. And that's c equals 1. So let's draw c equals 1. And then we're supposed to draw for 2. So that's going to look similar, but now that's c equals 2. And then finally, c equals 3. Okay, and again, is this a perfect parabola? No, but there's no way I can do this on a computer perfectly with drawing c equals 3. Any questions at all? Any questions at all on these level curves? So just a note, I didn't ask you to do this, but I think it's good to understand. If you, let's say you were hiking and you were walking along a level curve, what does that tell you about that hike? What does that tell you?
Uphill or downhill?
Exactly, exactly. You're walking flat, okay? You could take your grandmother on that hike. Does that make sense? Is that clear? On the other hand, let's suppose that you did this hike, like there, from low to high. What would that hike be like?
Not one you would want to take your grandma on.
Right, right. That'd be the hike I did yesterday, by the way, which was straight up the mountain, not on trail. Okay, the peak was beautiful at the top though. So again, that you're going as steep as possible. Does that make sense? Whereas if you're going on a level curve, it means that you're not even going anywhere. Okay, in terms of altitude, you're staying the same altitude. So level curves mean that the altitude remains constant. Okay, the level curves are important, but the line I drew is also really important. We're going to have an entire day just on that, on how do you get that curve given the level curves, and not just visually drawing it, but mathematically and algebraically in calculus. But not today. And you're going to need derivatives for that. Okay, any questions on the first part? Okay, let's go to the next one, and that's the only one that's drawing. Now, describe in words used previously in this class the domain of the function below. So first thing, we have f of x by z equals x squared minus y squared over 1 minus x squared plus y squared minus z. And if we want to find the domain, and hopefully you're used to this from algebra, is that when you want to find a domain of a function and it's a quotient, what do you focus on?
The denominator,
Yeah, what must the denominator not be?
0.
0. And you should also check, which is a very quick check, that there's no funny stuff like square roots that might mess things up. Does that make sense? Or logarithms, because those can also mess up your domain. But for this example, the only thing that can mess up the domain is the denominator. So what I'm going to do is I'm going to set the denominator equals 0 and realize that's not the domain. So let's do that. So I'm going to write 1 minus x squared and then y squared minus z squared equals 0. Any questions so far? Okay, now I told you, you must use words we used previously in this class. Okay, so this, we need to identify what this is. And to do that, I think it helps to add x squared, subtract y squared, and add z squared to both sides, and then switch the order. So I'm going to rewrite this. In fact, I'll do it this way. Copy paste. And what I'm going to do is I'm going to say, I'm going to take that these guys, get rid of them. Wonder if it'll let me do this. We'll find out. Yeah. And then switch the signs. Any questions so far? Okay, so now I have a question for y'all, because I told you how to use words used in this class, okay? And that is, what is this shape? X squared minus y squared plus z squared equals 1.
That's a saddle, isn't it?
Okay.
Isn't it a hyperboloid?
Yeah, it's
Oh,
hyperboloid.
oops.
How many sheets? 1 or 2 sheets?
1.
Yeah, this is 1 sheet because there's only one minus on this one. So what we can say is the domain is the set of all points that do not lie on the hyperboloid of 1 sheet shown above. I'm gonna just write above. Any questions on question 2? Okay, so I'll try to do, if I can, is I'll always try to bring in a little review if I can of a prior section. And there's your review, is you gotta remember that that's a hyperboloid of 1 sheet. So that's what I meant by in words used in this class, and those are the words. And notice that they do not lie. So it's not the hyperboloid, it's everything but the hyperboloid of 1 sheet. Any questions on this? Okay, finally, question 3. Find the equation of the level curve to f of xy is equal to 2 minus x squared plus y that contains the point 3, 6. All right, so the idea here, and by the way, I basically stole this one from the book. That's a good way to study is, you know, look at the book's problems. I just grabbed one from the section of the book and it had this one, but it looked pretty good. I think I changed the equation a bit, but kind of the question is the same. Okay, so the first thing we should do, since we want the level curve, is we need to find C. This isn't hard, but how do we find C? Yeah, we plug in. We plug in. So let's do that. We have 2 minus x squared plus y, and we're doing 3, 6. And let's go ahead and pop that in. So we got to plug in 3 and 6. Get 2 minus 3 squared plus y, and y was 6. Okay, and I tried to make it nice. So 2 minus 9 plus 6 is what? It's not supposed to be too hard. This is arithmetic, guys.
It's negative
It's
1.
-1. Okay. And that is equal to C. Any questions so far? Okay. And again, just like the first question, where does the C go?
Where f of x comma y is right now.
Exactly. So we can write -1 equals that. So let's write it out. So -1 equals 2 minus x squared plus y. And we should clean this up. You know, we're trying to make this a function. So let's clean this up on the next line. Get this as a function, so we can say y, we just subtract 2 minus x squared. And we get y is equal to x squared minus 3. Just by solving. And there we go. We found the equation of the level curve. Any questions at all on the quiz? Any questions? All right. I got a tough question for you now. Let me pop in what we're doing now. Get to that. Okay, who remembers the definition of a limit that you learned in first quarter calculus? See if you can tell me, write down the definition of a limit in the chat box. I know it's been a little while, but you all had it. Whether you had it at LTC or you had it somewhere else, you all had the definition of limit. And it was formal. Let's see if you remember. Yeah, that thing. Let's see if you can put it in your box. Victor, you're talking about the definition of the derivative. The limit definition of the derivative is different than the definition of the limit. So as Jacob mentioned, there's an epsilon, there's a delta. Those two words have to be in there. The word thing doesn't, though. See if you can remember. Because we need to define the limit, which I'll do. I'm not asking you to do that. We need to define the limit for multivariable functions. Okay, and in particular functions of two variables, which I'll get to. But let's see if you remember the definition of a limit for just regular old functions that you get in first quarter calculus. It was your favorite part, I think, right, of the whole class? I don't see you all jumping in, but hopefully you're all typing now. Okay, find the lowercase delta such that the lowercase epsilon lies between a certain range. And you get the idea, but that's not the full definition. Definition is, you know, it's strict, but not a lot of choices. So that's the idea of it, but the actual definition. Now we got a couple of people that have written down the limit definition of a derivative, which is different than the definition of a limit itself. So
Maybe you should just tell us.
What's that?
Maybe
I
you
know, I
should
was
just
hoping
tell.
maybe you know, and I will, but I wanted to give you a shot to try and bring in your brains and see if you can sneak it out. Uh-huh. Okay, we got some long answers. Most of your stuff. All right, looking it up is not getting it from your brain, by the way. Okay, let me write it out because I don't see anyone just remembering it. And again, I didn't say go look it up on the internet. That's a whole different thing. Okay, so let me remind you of the definition of limit. Okay, so first thing is f, and I'm going to write f in particular instead of what you usually would write, which would be f of x. F has a limit at a domain element if for any epsilon, I'm going to use the full word because it's too much of a pain to type it in to get that epsilon on the computer. For any epsilon greater than 0, there exists a delta greater than 0 such that if another domain element, so now I'm using the definition of a function so that we can very easily move this to multi-dimensions. You know, you didn't call it domain element, you called it x, but I don't want to call it x. I'm going to call it domain element. It's the same thing, right? For one variable. If another domain element, such that if another domain element is within delta of the given domain element, this original one, then the function evaluated at the original domain element and the function evaluated at this other domain element are within epsilon from each other. Okay, that's the wordy way of writing it. Remember that within epsilon from each other, that was the absolute value of f of x minus f of c. That's the same thing as the distance between the two being within epsilon of each other. Does that make sense? Okay, and similarly, if we looked at being within delta, that's the same, that was what we had before, is that x minus c was less than delta in absolute value. So absolute value was a word for, was a symbol for distance. So the reason why I wrote it this way is this way works for the one variable functions that you got in your first quarter calculus class, but it also works in what we're doing today. And what we're doing today is now let's look at functions. Let's look at functions of 2 variables, or even 3 variables or 4 variables. Any questions on that? Okay, so for 2 variables, for one variable you've already learned, so I'm not going to rewrite that. I'm going to write for 2 variables. So let's boldface this guy, since it's a big definition. Okay, so the first thing is I need to write down the limit. And wonder if I could do this without the sum. No, didn't want the sum. Missed it. That one. There we go. So we want the limit as, so now what we don't want anymore is we're not having the limit as x goes to c. Now we're going to have the limit as x naught comma y naught, sorry, x comma y goes to x naught y naught. Of f of xy is equal to, is it going to be a point or a number? What do you think?
A number?
Yeah, it's a number. Because remember, the domain of a function of two variables is a point. The range is a number. So f of a point is a number. So that's going to be a number. We usually use letter L for limit. Okay, so that's the first thing. That's the symbols used to talk about the limit. If for any epsilon greater than 0, there exists a delta greater than 0. Such that if, now we need to make these equations happen. So we want to be within, the point has to be within delta of the other point, such that if the distance, so I'm going to use the absolute value for the distance, okay, or maybe magnitude is even better. So the magnitude of the vector x comma y minus the vector x naught y naught So if the magnitude of that vector is less than delta, then the absolute value of f of x y minus f, minus f of x naught y naught, we take that absolute value and that better be less than epsilon. Any questions on this so far? Okay, I have a question for you. If I give you a point x naught y naught, and I say, what are all the points such that the magnitude of xy minus x naught y naught is less than delta? What is that? In a word that even a 4-year-old would understand. What is it?
Difference?
Not quite, it's not different. A 4-year-old may not understand the word difference. This is one a 4-year-old understands. Every 4-year-old, usually 2-year-olds understand, in fact. Just a hint, that's how simple this is. It's the first math geometry word that any child learns, or most child learn. No? No, lines are hard for them, by the way. 2-year-olds don't get lines.
Point?
No, points are tough too, actually. Points are really abstract. Should I tell you? It's a circle.
Oh,
It's a circle. If the distance between from a point is less than delta, those are all the points in a circle, within the circle. Does that make sense? Okay. A little better be disk, but I wanted to go for the 2-year-old answer, the baby answer. So it's all the points within a circle. Does that make sense? Okay, so I want to tell you something. Here's something you're not going to have to do. You're not going to have to do the epsilon delta definition to do proofs. Okay, and by the way, you should feel happy about that. You know why?
it's hard.
Yeah, I think hard is not a strong enough word. Brutal
Hellish?
is a better word. Brutal. It's
Okay.
brutal to do a proof like that. Okay, to do a full epsilon delta proof in multiple dimensions is brutal. I will tell you, I don't know if we have any math majors, but when you hear the course called Real Analysis, that's when you do it, and it is brutal. So we're not going to do it, but here's what we are going to do, which I'm not going to prove, but the theorem. And the theorem makes this definition much easier to deal with. So I'm going to give you two theorems. The first theorem is only kind of a theorem, but it's going to be good enough for our class. And the second theorem, so basically the first theorem says you might get lucky and then life is easy. So the limit of any nice function, actually write down to find the limit. To find the limit of any nice function, just plug in. Okay, it's not a rigorous theorem, but it's going to work for most of what we do in this class. Not all, not today actually, but after today it'll work for almost everything we do. Okay, so let me boldface that. Let me give an example. And that is let insert function f of xy equal x e to the y minus, get over there, minus cosine of x plus y. Find the limit of f of xy at the point and x, yeah. Pi over 4. Let's didn't do the over. Let's do it one more time. So now pi over 4. Comma 0. Okay, so given the theorem, is this a nice function? Are there any big issues with this function about not having a limit just by intuition? What do you think? X e to the y minus cosine of x plus y. Are there any issues?
Maybe the cosine or the exponent.
Does cosine ever have an issue with limits?
Um,
Just think one
well,
variable.
it can't approach beyond one, right? Unless it's multiplied by a constant.
Okay, remember, you're talking about a limit. You're talking about what you can plug in, not what you get out.
Oh, okay.
Are there any issues on what you can plug into cosine?
No.
No. How about exponential? You were worried about exponential. How about e to the y? Does that have any issues? Like when you took first quarter calculus, was f of
In
x
terms of
equals e to
domain,
the
no,
x? Were there
no.
any issues with that in terms of limits? Not really, right?
No. Yeah.
Yeah, this is a nice function. The product and difference and sum, but it's a bunch of, x's and e to the x's and cosines. Those are all fine. This is a nice function. Does that make sense? Okay, so what are not nice functions? Where do things go wrong in terms of limits? Or could they go wrong? Yeah, if you have a rational function, like a over b, something over something. Another one is square roots can go wrong, right? Because you got a problem with negative numbers, all kinds of problems. Okay, logarithms go wrong at 0. Hopefully you know that. So when I say nice functions, it means that a function where nothing in it goes wrong, any of the bad stuff that happens. Tangent of x, right? Tangent is not a nice function because that has problems, right? It has an asymptote. Is that clear? On the other hand, this one is nice. So I'm going to use this theorem. We have a nice function. And again, the theorem is, maybe I should do this. I'm going to put the theorem in quotes. So what I'm going to say, it's a good rule of thumb might be a better word than theorem. It's going to be quote theorem. It's not a true theorem, but it really works for just about everything we do that is a function where it doesn't go wrong. So what do? The hint is it's easy. Yeah, we plug in and we get pi over 4 e to the 0 minus cosine of pi over 4 plus 0. And the answer is the following. So it's going to be pi over 4 e to the 0, which is pi over 4. And then you got to remember what cosine of pi over 4 was. That was root 2 over 2. So we get is that the limit, let me just write the limit is these guys. This first. And then this. So it's pi over 4. And then it is minus, and then we have a fraction again, square root of 2 over 2. And that's it. Do you agree that was easy? Okay, so if you're lucky and you just have a nice function, limits are really easy. You just plug in, you're done. Okay, any questions on this kind of theorem, or rule of thumb is a better word? Okay, now we got to deal with not nice functions. Okay, not nice functions mean that you have denominators where you have a 0 in the denominator. You might have a log of 0. You might have a square root of things that go towards negative or something like that. So stuff where things go wrong. Okay, tangent of 0 is another one, or say tangent, let's see, not tangent 0, tangent of pi over 2. So limit it, if it goes towards pi over 2, we're in trouble. So there's some functions that go wrong. Okay, any questions on kind of what I mean by goes wrong? Okay, so now comes a big theorem. And I'm not going to prove this one definitely not. Way too hard to prove, but you can believe it. And that is, it is enough to show that the limit exists for any curve. Actually, I want to say for every curve that goes to that point to arrive at the fact that the limit exists. Okay, and that might be a little hard to understand. And again, I'm not proving this because it's hard to prove. Too hard for this class. So it might be helpful to see a little picture. So let me do a picture. We can talk about it. So let me do a drawing. Okay, so if we have we're doing the XY plane. Let's say we have a point. And what the limit definition says is that what we have to do is we have to take just 1 second. That's close enough. We have to take a circle, pretend that circle's center is the point. I know it's not perfect, but it's as good as I can get. So we have to take a circle around that point and show that the function is close to the function at the point anywhere in the circle. So here's the idea, is that I can take, if I consider any possible curve that goes to that point, and I show that if I take that curve and I take the limit as you move along the curve to that point, and I do that for every single possible curve, and I always get the same limit for every curve I look at. So that's one curve. Let's look at another curve. So there's another curve that goes to the point. So if both of those have a limit as we go to that point along the curve that's the same and defined, and not just both of those, but any possible curve I can draw, then I can say that the limit exists and it is that value. Any questions on the idea of this? Okay, this may sound like it's even harder than the original definition. It's actually not. Why is it easier to think about a curve going to a point than the circle around the point or the disk around the point? Why is it easy to look at a curve? Any thoughts? And it comes from something we did a week or two ago, I think 2 weeks ago. Okay, I don't see anyone jumping in, so let me explain. So the idea is that if you have a curve, you can define it as x of t comma y of t. Any questions on that? Okay, you can define it parametrically. So then as soon as we think about this curve parametrically, then if you plug in the function, so let's do that. And we look at f of x of t, comma y of t, why is that going to be easier to work with? Why is f of x of t comma y of t easier to work with than f of xy if we're looking at going towards the point? Yeah, the function of point gives you a number. It may not, remember, we might have 0 over 0. Does that make sense? So it may not give you a number, actually. The limit doesn't have to be defined. The function doesn't have to be defined at the point at all for the limit to exist. So we can't evaluate
We
the
can
function.
incrementally approach the point, maybe? I don't know.
We can do that, but I'm looking for something else. Has to do with the t. You don't see it? Okay, so the original function is f of xy. Let me remind you. The original is f of xy. That's a function of two variables, right? But as soon as you write it as f of x of t, y of t, it's not a function of two variables anymore. It's a function of one variable, t. Do you see that? And if you have a function of one variable, then you can use what you learned in first quarter calculus, how to find a limit, right? And that's either doing a little algebra, sometimes it's L'Hopital's rule. Do you remember that stuff? So you do that, and if you can show that you get the same value no matter which parameterization you have, as long as you're going towards the point, then you've proven that you have a limit. Okay, and it goes the other way around. If there are two curves such that as you move along towards in one way, so let's say Caesar is doing this curve here and moves along here and finds the limit is 7, and Victor goes for this curve and finds the limit is 3, what can you say about the limit of the function? Yeah, it does not exist. So if, just like when you learn in first quarter calculus, if going from the left and going from the right give you different answers, it does not exist. Well, here it's not left and right. Here it's one curve versus some other curve. And if you can find any two curves so that you end up with different answers, then you can say the limit does not exist. Or if you can find one curve at which the limit doesn't exist, on that one curve, the limit doesn't exist. Any questions on this idea? Okay, so now let's do some examples. And let's start with a new page. There we go. Any questions so far? Okay, so let's go for, how about the limit? Let's go over here. And let me do limit. Yep. So limit as xy goes to 0, 0. I want to actually write it out. So let's make it a fraction. And let's go xy over x squared plus y squared. And let's make it a little bigger so you can see. Okay, So the first thing I have for you guys, is this a nice function that we can just plug in and we're done?
No
Okay.
function is nice enough for that.
This is not a nice function. If you plug in 0, 0, you get 0 over 0, and you know things are bad. Do you all know that? Okay, this is not a nice function. There are nice functions. This isn't one of them. Okay, so you can't just use that first theorem that says plug in and you're done, and that was wonderful. Okay, so that means we got some work to do. And by the way, there is no just algebra you can jump into. So what you could do is you can try, well, let's start going through a curve and see what happens. Well, let's try the, what are the easiest curves, especially if you have to write parametric equations that go to the origin, by the way?
Lines?
Yeah, lines, but what's the easiest line? How about the
A
x-axis?
horizontal one?
Yeah, how about the horizontal? And you could choose whether you want to come from the left or the right. Let's go from the right, because that's the easier one. So let's let x of t, comma y of t. I'm going to write it in vector form, comma y of t is equal to, well, if we're looking at a line from the horizontal line that goes towards the origin, we can say this is t, comma 0. Isn't that the easiest of all possible curves that go to the origin? Okay, so now what we need to do is we need to plug in. I'm going to copy and paste and change what we need to change. So first thing, it's now t goes to 0. Is that clear? So x is t times 0, because y is 0. Okay, we make a times sign instead of. And this becomes an t squared, the denominator becomes t squared plus 0 squared. I'm just going to write t squared. Well, what is this limit? Not 1 over t, actually. The hint is it's really easy. It's just 0. No matter what t is, this is always a 0 function, right? If t is a half, plug in and you get 0 over a fourth. That's 0. If t is a millionth, well, plug in and you get 0 over a million, or 0 times a million. Still 0. No matter what you do, you always get 0. This is just 0. Any questions on that? Okay, what is the next easiest line to parameterize?
A line with a slope of 1.
There's an easier one.
The y-axis?
Yeah, the y-axis. Isn't that easier?
Yeah.
So I could literally just copy and paste and, I get zeros for the x's. I'm going to have a 0 for the x instead of the y. So now I can just do this. This t becomes a 0. This 0 becomes a t. And now it's, instead of t times 0, it's basically the same, 0 times t. Now what is this? What's that limit? Yeah, it's still 0. So we've now got 2 different curves such that when you take a limit, you go to 0. Does that mean that the limit equals 0? What do you think?
No.
No.
Now, how many do you have to show are the same to show the limit actually equals 0? And the theorem says all.
Infinitely many?
Yeah, infinitely many. It's a bad infinite, by the way. It's not even countable infinite. So this does not show the limit as 0. So here's the deal. At this, what you have to do is, and this is probably the hardest part about this whole section, you have to think, I think this exists, or do I think it doesn't exist? Does that make sense? So if you think it doesn't exist, then we're going to try and find other curves and hope we get something different. If you think it does exist, then we're going to have to prove it exists in some interesting way. I am going to tell you, because you don't have intuition yet, because this is the first time you see this, is let's think it doesn't exist. And let's try something different than the axes. Because what the axes are doing is it's nuking out the numerator. So let's do the y equals x line, okay? So now let's do, I'm gonna do the same thing, but now I'm not gonna let it be t comma 0, I'm gonna let it be t comma t. That's y equals x, right? And then now what we're gonna have is we're gonna have t times t over t squared plus t squared. And what do you get when you take that limit?
As t approaches 0?
Yeah, that's what it says, t approaches 0.
Yeah. Isn't it undefined?
No, it's very defined. Simplify. Do algebra, that's a hint. What's t times t?
Oh.
T times t is t squared. What's t squared plus t squared?
T squared.
Yeah, 2t squared. So what's t squared over 2t squared?
1/2.
1/2. Take a limit as t goes to 0 of 1/2 and you just get 1/2. So equals, and I'm going to have 1/2. All right, what can we say now? Why is that good? You say the limit, but what about it? Why is it good? Yeah, I'm just going to write D, N, E. When you had Bruce, did Bruce use D, N, E?
Yes.
Yeah, okay. I think that's pretty common. I use D, N, E also. I tend to do capital D, N, E. I think the computer does capital D, N, E, so that's why it's better to get capital. Yeah, I'm not sure if the computer forces it to be capital. Okay, so this limit does not exist because the theorem says that if you can find two curves such that the limit goes to a different value as both curves go to the point, the limit does not exist. Any questions on that? Okay. The hard part is deciding to try and find two curves that do that, because the first two didn't work. They got the same value. Okay. All right, let's do another example. So I'm going to do the same idea with another example. So let's see if we can see what is the limit as xy approaches 0, 0 of x cubed plus y cubed over x squared plus y squared. Okay, does this look a whole lot different than the last one?
No.
Not really. Okay, and that's what makes this hard, by the way. This is completely different. And that's why this is hard, because it doesn't feel different at all. So here's the deal. We only have 9 minutes, like 14 minutes left. So I don't have time to go and do a bunch of curves and give up. But I will tell you, if you go the x-axis, you'll get 0. If you go the y-axis, you'll get 0. If you go the line y equals x, you get 0. Those are the 3 that we tried. Maybe you could try y equals x squared, and guess what you'll get?
0.
0. Okay. Is that enough to say the limit exists?
No.
No. Okay. But we're going to say we tried a whole lot, and just trust me, if you tried a lot, you'll get 0. So we're going to think maybe the limit exists. So if the limit exists, it's a completely different strategy. So let's write this down. If the limit big. If the limit exists, then
Get off of me, dog.
try using polar coordinates. Okay, why do you think polar coordinates might help us? Why is it going to simplify things? Any thoughts? Okay. What does it mean? What does it mean if you have a curve going to the origin in polar coordinates? What can you say about that curve?
It has a radius of 0.
Yeah, or in particular, r tends to 0. Does that make sense? The curve isn't 0, but r goes towards 0. You see the difference? Because remember, we're talking limits. So it's not that r equals 0, but r goes to 0. And theta can be anything. So by turning into polar coordinates, we take a 2-variable question or a 2-variable limit question and turn it into a single limit question. Okay, now this doesn't always work, but it usually works. So let's do that. So we're going to take a limit now as r goes to 0. And now what we need to do is turn this into polar coordinates. Well, x cubed, who remembers what x cubed is in polar coordinates? I'll start you off. R. Do you remember x cubed in polar coordinates? It's actually r cubed cosine cubed theta. Because we're cubing it. And who remembers what y cubed is? Yeah, same idea. It's r cubed sine cubed theta. It's going to be r cubed times sine cubed of theta. Why is this nice?
Why is the bottom a T?
Because I haven't changed it yet. I copy and pasted so I didn't have to redraw the limit thing. So why is this nice? Oh, I didn't say it. Sorry. X squared plus y squared is r squared. Forgot to mention that. Yeah, we can cancel out an r squared on the top and the bottom. So it's going to be equal to the limit as r goes to 0. Still have that. Of, and if we cancel that, we end up with r times cosine cubed of theta plus sine cubed of theta. All right, now we're taking a limit as r goes to 0. What is this limit? Yeah, this limit is 0. And notice what we did not do is we didn't pick some special curve. We just changed the coordinate system that we're looking at. And now we have a single variable. Theta's in there. And the important thing, by the way, and you always have to check this, is that cosine cube theta plus sine cube theta that's a nice function. Doesn't matter what theta you have, you don't get things like infinity. Had it been tangent, you got to worry. The tangent goes to infinity. But cosine and sine are nice functions, which means you have 0 times a nice function, and that's just 0. So that's a proof. So therefore, the limit is 0. Any questions on that? Okay. Just a note, we can draw these guys to see what they look like. Using Calplot 3D. So for example, if I do the one I just looked at, that was x cubed plus y cubed. Divided by x squared plus y squared. And if you look at the origin, is there anything funny happening at the origin that you're looking at on this surface? What do you think? Or does it just look like a nice surface?
Just looks like a nice surface.
Yeah, it's just like, looks like a nice surface. What this is not showing, or maybe our eyeballs aren't good enough, is it's not showing the hole at the origin. There's actually a hole at the origin. Do you see that? Okay, the hole's so small, right? It's infinitesimally small, we can't see it. But the limit exists. Do you see that? Whereas if we do the other one, where it didn't exist, let's see what that looks like. We do xy over x plus squared plus y squared. Now what's happening at the origin? Does it look nice or not? What do you think? Yeah, now it's got problems. Do you see? Do you see what at the origin it's got ups, it's got downs. Who knows where it's going to hit? And it doesn't hit anywhere. That's why. It's all over the place. Do you see the difference? It's like cut up and sliced at the origin. Okay. And if you zoom in, which I think I know I have to do. Move my zoom thing. No, that's not true. There it is. Zoom in. All right, now we're zooming in at the origin and we can see bad things are happening. Okay. If you zoom in at the origin and it does exist, you're gonna see a plane and it turns out. This is not a plane. Any questions on this idea? Okay, I'm going to quickly do these last pieces. We don't have a lot of time. Just going to state the definition. There's not much to say. A function f of x comma y is continuous at a point. I'm going to call it AB. It's easier to type. If. Do you remember what it meant to be continuous for a single variable function? Yeah, either, well, the limit may not exist, but there's another possibility also. Either the limit doesn't exist or the limit is not equal to the function evaluated at the point. And it's the same actually. Okay. So if both of the following are true. So one, the limit exists. And let's call it something, how about L? Equals L. Okay. And number two is that f of AB must also equal L. And that's what it means for a function to be continuous. So the hard part is the limit. Plugging in is easy. If you can't plug in, it's not continuous. So that first one where the limit exists, that first example that we had, that guy. Was this a continuous function at 0, 0? What do you think? Okay. The idea is we found the limit existed. The limit doesn't exist, so it's definitely not continuous. It's over. How about the second one? Is this a continuous function? Okay, the limit exists, but did you try plugging in? Plug in 0, 0, what do you get? I get 0 divided by 0. What is 0? What's 0 divided by 0? It's undefined. This is not a continuous function. Is that clear? On the other hand, this guy, is that a continuous function at 0, 0, or anywhere actually? Yeah, this one's continuous. The limit exists. You plug in the point, you get what you want. There's no issues. Continuous functions don't have issues. That's the good news. There's a continuous function. Any questions on this idea? Okay, what I didn't go over, but there's really nothing much to say, is that if I added a z here and I did f of x, y, z, it's the same definition. You do the same thing, it's just more work. Does that make sense? So if it's 3 variables, because we're about out of time, if it's 3 variables, then it's not really any different. Okay, proving a limit exists is actually really hard. You could try spherical coordinates and hope. That's your only chance. Okay, just like we did polar coordinates. So to prove a limit exists, go for spherical. To show it doesn't exist, try different curves, but now it's a x of t, y of t, z of t, and hope that you get different answers or undefined answers. But it's the same. There's not much to say. That's why I spent time today on it. Not because you're not responsible, but there's nothing to do. Just more writing. So we're out of time, which means I'm going to drop the recording.